Hello students and welcome to BMM3521 Engineering Mechanics Fluid Mechanics Lab. Uh, we have got experiment number 2, which is the investigation of flow pattern over immersed bodies and boundary layer or boundary layer theory. So these slides were prepared by Dr. Ahmad Shukri and Dr. Ahmad Yusuf there. They have to be acknowledged, and I am the one who is making some addition or version changes. So you are given two types of lab sheets. One is flow over immersed body and one is boundary layer. So let us move on to the experimental data which has been provided to you on Kalam as well. So experiment number 1 is about flow pattern of symmetric aerofoil at different angle of attacks. So we have got three tables, table number 1, 2 and 3. They have got different angle of attack, attack at 0, attack at 30 and attack at 45 degrees. The fan speed is given. The fan speed does not have any unit because it was only a knob that was used. So consider these as only a unit of fan speeds or just primary fan speed values, measured values. Whereas for the head pressure, in terms of height, we have got initial height which is 137 millimeters, and then the remaining height is given in terms of millimeters as well. So using this you will be able to calculate delta H or the change in height. So here is experiment number 2, flow over flat plate. It can either be a smooth surface plate or it will be a rough surface plate. And then in the table you've got the plate distance given from 10 to 80 millimeters, and then you've got the head which is given at specific boundary layer thickness from specific distance which is also given. So the measured values of head are given for plate distance from 10 to 80, both for smooth surface and for rough surface. So next we are going to move on to the theory of the boundary layer a little bit. Okay. So the objective of this experiment is to design a complete measurement technique for fluid flow and measure the drag and lift forces which are generated, and they are applied on an aerofoil shape only. So we are only going to consider lift and drag forces for an aerofoil shape. Now to determine the velocity distribution of the flat plate, for the flat plate, so we go to flat plate and then we need to determine the boundary layer thickness and the velocity distribution. Then to determine the boundary layer thickness for flat plate subjected to longitudinal flow for smooth and rough surface. So these are the objectives for the two lab sheets which are given. So the theory of boundary layer effects were given and first presented by Ludwig Prandtl, okay, in the early 1900s, and he was able to basically provide the solutions to the equation that were not previously observed for flow effects on wings and stalls. Now the Prandtl basically say that we have got some inertial and viscous forces which change a layer from very near surface to very near far to a very region which is far away from the surface. So there is a difference between the viscous forces and their effect for velocity profile which is near to the surface and which is far away from the surface. Now the particle which were right next to the surface stick to the surface. So if you've got a plate and then you've got an upstream velocity, then the particles that are going to basically be near to the surface, there will be something which will be attached to the surface. So exactly at that point the velocity will be equal to 0 because the particles stick to the surface. The particles just above the surface are slowed down because of their collisions or due to the viscous effects. These particles slow down the flow above them, so then the flow particles is slowed down because of the viscous effects which generated from the particle which are stopped. So the farther one move away from the surface, the fewer the collision affected by the object surface. This creates a thin layer of fluid near the surface. So this creates a thin layer of fluid which is near to the surface, and this is called a boundary layer. So this thin layer is called a boundary layer. In this boundary layer the aerodynamic forces are generated. Okay, so we have got the lift force and the drag force which are generated, causing a resultant force as well. So these aerodynamic forces are called the drag force and the lift force, and this is a figure for the boundary layer. So when the fluid flow through an object, the object will experience a resistance force that prevent the object from moving into its direction. So anything which is moving, okay, it is a body or something, and it is moving against a flow of air or against a stream of air, okay, then basically the body is going to experience a force, and the distribution of force is given such that the flow direction is in this direction. This is our body, this is an aerofoil shape, and then we've got the drag force which is dragging the body backwards, and then there is a lift force which wants to lift the body upwards. So these are the total aerodynamic forces which are generated. Now the figure also shows the resultant forces of the drag and lift force. So there is a resultant force which is generated in this direction. So both of these three are vector quantities. So you might have gone through this theory in fluid mechanics 3 as well, that you've got an aerofoil and you've got an upstream velocity fluid which is coming. Okay, now the angle that it makes with the upstream velocity is very important, and that angle basically decides what is going to happen at the back end of the aerofoil. So in this region, basically what happens is that as you change the angle of attack from upstream velocity, then what happens is that the separation occurs, the flow separates from the body. When the flow separates from the body, then pressure or wake regions are created. These can be turbulent wake regions. Now these wake region causes a pressure difference at the upper part and at the lower part. So what happens is that when a stagnation point, the dividing streamline and the stagnation point move down, hence more air flows above the wing, and thus there is a decrease in velocity below the airfoil. So there is more amount of airflow above the wings, and there is less amount of air and less velocity below. So Bernoulli equation states that when there is a decrease in velocity, then the pressure lift will increase, and this increase in pressure will cause the lift force to increase, and that is why the lift is created onto the aerofoil. So this is a little bit theory on the aerofoil and how the angle of attack changes the stagnation or separation points and how wake region is created. So in order to create or in order to determine the forces drag force and the lift force Fl, we have got a dimensionless quantity called CD, coefficient of drag. Okay, using coefficient of drag and coefficient of lift, we can basically calculate our Fd and Fl for our body. So in our case, for our experiment, we have these dimensions of the airfoil. So we already have the coefficient of lift and the coefficient of drag already obtained. So using these dimensionless quantity, you will be able, and it will help you to calculate the drag force and the lift force. So there are different engineering scenarios, such as here is a case of a duct, and what they are saying is that the flow in the boundary layer can be turbulent. Okay, so it can be turbulent and it can be laminar, but it is very difficult to distinguish between laminar and turbulent boundary layer. It is not very easily specific. So the transition, there is a region called transition region which occurs. Now it is very difficult to predict the laminar boundary layer and the turbulent boundary layer because it depends on a number of things. In many real flow situations, it depends on the pressure gradient, number one. Number two, the surface roughness. Number three, the heat transfer. And then number four, the body forces. And number five, the free stream disturbances. So in many real flow situations, the boundary layer develops over a long, essentially flat surface. A qualitative picture of this boundary layer and the transition is given. We have got the temperature infinite, upstream temperature, the upstream fluid flow velocity. So there are a lot of what you call parameters which are involved. Depending on the roughness of the surface is one of the factors. So roughness is something that you are going to consider, and you are going to see the difference that a rough surface and a smooth surface creates on the boundary layer and the boundary layer thickness. So when we talk about a flow boundary layer, okay, then they say that at near the surface region, there is, due to no slip condition, the fluid is assumed. It is assumed. It cannot be assumed to be inviscid. Okay, which means that we have to consider the viscosity effects near the region. However, when we create a boundary layer, okay, then this region which is outside the boundary layer, we can assume that this is inviscid, which means that the flow viscosity effects can be negligible. Now this happens, the requirement for boundary layer to be thin is that the Reynolds number of the body is to be very large, which is 10 to the power 3 or more. So a Reynolds number should be greater than 10 to the power 3 or more for these conditions to be realized. So under these conditions, the flow outside the boundary layer is essentially inviscid, which means that the viscosity effects are negligible. However, within this boundary layer, the viscosity effects are present, and they are the driving mechanism for the layer. So using these equations, you will be able to calculate the dynamic pressure, okay, and Reynolds number, the density, and the viscosity are given for the fluid. So we are going to move to our methodology. The video for the methodology is given by Mr. Padli, our GP. So you can go and see the video regarding that. So the experimental setup for our experiment number 1 is given in your lab sheet as follows. The experimental procedure for you is given as well. First, we attach the airfoil model, then we screw it to the airflow according to the angle of attack. So first we are going to use 0 degrees, and later on we can move on to 30 and 45 respectively. Then we are going to switch on the radial fan so that the air flows through the our aerofoil. So we have got an upstream velocity. Then the radial fan speed is controlled at an initial speed of 12, and then it increases as given in the experimental data. The readings are then recorded and tabulated. The smoke controller is given as well, which is used to emit the smoke into the flow so that you guys can view how the flow occurs and how the boundary layer might look like. Then the radiator or radial fan speed is basically increased until 19, and you have to repeat the same steps for 30-45 degree angle as well. So here is an live picture of 0, 35 and 45 degree angle of attack aerofoil, and then we've got a knob which is used to change the angle. So this is our bench for our testing. We've got the airfoil model, okay, it is placed here, and then we've got the manometer readings, okay, this is the bench to observe, and then we've got a smoke controller as well, a knob, so that we can control the smoke, and then we've got fan controller available as well. So experimental number 2 is a little bit different, but we've got a flat plate which is either smooth, and then we have another plate which is very rough. So we will be taking two set of readings. So the experimental setup is shown in the next slide. The smooth surface plate is inserted into the airflow bench. Then the first distance is taken as 0, and then the following distances are taken. The pipette tube is connected to the vernier calipers. The pipette tube is first touched to the surface of the flat plate as the first data. So this gives us the pipette tube readings. The radial fan has been then turned on and data are recorded. The distance of the plate is taken from 0, and then it is increased according to the data which is given to you. So here we've got our manometers, okay. We've got the pipette tube, then we've got this test bench. So here is an example of a rough plate which is attached, and then a smooth plate which is attached. So we are going to move on to the results. What should be included in the lab report? So for experiment number 1, which is the symmetric airfoil, you have to plot the drag and lift forces at various angle of attack, okay. So you have to basically plot the force FD and FL separately with respect to the different speeds, okay. And please mention the units, and then please mention the force units, and then make it different graphs for different speeds, something like that. Make sure that the distance, there is enough y-axis distance, y-axis spacing is very well, so that the graph can be seen separately. Okay, some students I have seen they mix up together because the y-axis scale is not correct. So make sure that the y-axis scale is correct. Sketch the streamlines of the airfoil at different inclination angles with separation and stagnation point clearly labeled. So basically you have to sketch the boundary layer, and then you have to basically also show the separation that could have happened. Next, we move on to the experiment number 2, flow over flat plate, rough or smooth. So you have to plot the head, velocity and Reynolds number separate graphs versus the boundary layer for smooth and rough surface. But make sure that the smooth and rough surface data is in one single graph so that we can compare or we can make a comparison. So basically you should have a smooth surface data and rough surface data for head, then same for velocity and same for Reynolds number. Plot velocity versus distance, so same goes for this. Then draw on the worksheet the speed distribution and boundary layer thickness for smooth and rough surface. So in the lab sheet you have got your plate, so you have to basically draw the boundary layer. So this is all the results and discussion that you have to submit.